Thanks very much for the invite as well. I really appreciate it. It's a great seminars you're organizing. Thanks for doing that. And yeah, it's great to be here to discuss this. So my name's Tim Duignan. I am a researcher at Orbital Materials now. Um, I used to be an academic here in Australia. I worked at Griffith University and University of Queensland. I did a postdoc at Pacific Northwest National Lab, working on basically physics, chemistry, and chemical engineering using quantum chemistry to run simulations of chemical engineering systems, things like electrolytes for batteries and that type of thing. And then I got really excited about neural network potentials a few years ago and started working mostly on them. And then, yeah, have switched to working in industry for Orbital, who I really enjoy. Sander, do you want to introduce yourself?
Yeah, I just graduated my PhD from Ghent University in Belgium, and I joined the company in January, so only been there for 6 months. I guess my job at Orbital is a result of my PhD, which was a hybrid between, I guess, the application of ML potentials and then exploiting them for enhanced sampling and all kinds of molecular simulations. And this is kind of also what I'm doing now at Orbital, basically, as we'll see soon.
Cool. Great. So, yeah, neural network potentials. I thought I would start from the very beginning, basically, which is all back at quantum chemistry, quantum mechanics, and chemistry and that connection. And this is an amazing connection, which is really worth kind of understanding yourself if you haven't looked through it. But basically, it turns out that the entire periodic table, the entirety of chemistry itself, can be derived from just one differential equation, right? The Schrodinger equation. And when you solve this, these kind of so-called quantum numbers pop up, which are associated with the different solutions to Schrodinger's equation. And they have this kind of natural grouping where you group them in one and then four and then nine. And if you double these for the two spin states the electrons can be in, you immediately get the two, the eight, and the 18 elements in the periodic table, right? So you immediately, the whole structure of the periodic table just drops out of solving this one differential equation. It's incredibly beautiful. And when I learned this, it just kind of enchanted me. And I wanted to understand more and understand how you could leverage this. And this has captured a lot of physicists, I think, who have always kind of thought that really chemistry is just a sub branch of physics. And we've always kind of wanted to make it that way, but we've never really been able to. So this is Dirac's famous quote. He said, the underlying physical laws necessary for the whole of chemistry are thus completely known. Approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems. So the whole idea is that chemistry is an application of quantum mechanics. And if we could solve the equations of quantum mechanics quickly enough, we'd be able to do incredible things. And many physicists have dreamed of this. It led to the whole discipline of quantum chemistry. And this is quantum mechanics, Schrodinger's equation. You get all of chemistry from it. Uh, and so the idea, which what I was working on at PNNL, was ab initio molecular dynamics, right? Where you have a simulation, you get the positions of all of the atoms. You use quantum chemistry, in particular, an approximation called DFT, to approximate that quantum chemistry. In particular, what you're trying to calculate is the forces, right? Which are the gradients of the energies. And then you use Langevin dynamics to update, or some other molecular dynamics algorithm, very similar to Langevin dynamics, to update the positions of the atoms. And then you loop this iteratively to generate a trajectory, right? A movie of how the atoms are behaving through time. And this is a very useful tool. There's kind of some problems you can solve with it about processes that happen on the kind of billionth of a meter and a billionth of a second time scale, right? Nanometer, nanosecond, um, which is very useful, but unfortunately, that's inherently limited, right? And there's a huge amount of stuff you can't do with this. In particular, you can't solve most of problems that are of interest to chemists practically or biologists, right? It's just too small and too short a time scale. So we really want some way around this. So in practice, the way computational chemistry works is you have this kind of hierarchy of approximate methods, right? So ab initio MD only works down here for the very small and very short time scales. For anything larger or more complex, we've developed all of this kind of toolkit of tools to address them. Things like classical molecular dynamics, continuum mechanics, and coarse-grained methods as well. And these work at these larger scales, but they're inherently much more approximate. They have a ton of parameters which need to be fitted. Very difficult to use them out of their area where they're well experimentally parameterized. So you can't make genuinely new purely theoretical based predictions. And this has always been like deeply unsatisfying to me, right? I've always felt that there should be some way of going from the ab initio, from the quantum chemistry to say something useful about these larger scale systems, but we've always been unable to really do that. And that's why I'm so excited about neural network potentials as a tool to potentially bridge these scales, really. And so the idea is very simple. You're just going to swap that expensive solution of density functional theory of quantum chemistry, Schrodinger's equation, with a neural network potential. And that's going to be trained on a big database of DFT calculations that have been done previously of forces and energies. And there's a ton of these now coming out, which is really exciting. You've got Materials Project was one of the earliest ones. And just recently, the other day, OMOL 25 came out from Lawrence Berkeley and Meta and some other people are working together, and that's a huge database now at really quite a high level of quantum chemistry, to the point that it should really be accurate enough to make some really quite precise, accurate predictions about a wide range of things if you could build models that are accurate to that level of theory, which it seems like we should be able to do. So this is a really exciting time. We now have huge amounts of data we can use to train these things on. And the field's kind of been exploding recently, right? So you had this kind of gradual growth in these things. So this is these are some universal models that have been released over the years. And this is the F1 score on a particular data set from MapBench on a particular subset of training data. And you can see that as these models have been added, we had early on, back in 2022 now, we had these very early kind of pioneering models. And then MACE MP0 was a big breakthrough where, along with the new model, they demonstrated that it had this kind of remarkable generalizability capability, right? And you could simulate large areas of chemical space that weren't necessarily in the training data, which was a really exciting breakthrough. And then you had the genome paper where they used it to make this huge database of material structures, of crystal structures. In Nature, which got a lot of attention. And then more recently, you've had this kind of explosion of these models, right? We're kicked off really by Orb-v3, which was a really exciting breakthrough where we showed that not only could you get, well, Orbital showed that you could get really good accuracy with a model that was non-equivariant, but also much more efficient in terms of speed and memory than previous models had been. And then there's this, flourishing of models all coming out all simultaneously, which has been really exciting. Followed up by Orb-v3, and now there's even new models coming out still. You had UMA just the other day trained on this new OML database. So yeah, very exciting times. There's now huge amounts of data here. There's a huge amounts of new models coming out, lots of architectures people are exploring and trying doing new things. So now the question I think becomes, what are we going to do with these models? Like, what's so exciting about them? What should we do with them? And one kind of area I think they're useful, one way of thinking about what they can do, which is kind of the naive way of thinking about it, which is how I thought about them for a long time, is as a kind of replacement for ab initio MD and for some classical MD. And I think that's exciting, and I think that's something that's coming and makes a lot of sense. And so I was just going to talk about that a bit, and then I'll talk briefly later about another way of interpreting them. So this is what I kind of originally was using them for. My previous work, I was very interested in electrolyte solutions, right? So ions and water, very important for batteries and many minerals, material science applications. And so I thought, well, we could just use neural network potentials to simulate liquid electrolytes. And that worked really well. You could get nice predictions of various things to do with simple electrolytes. But then when I saw the Orb paper come out that can simulate, so these things are now trained on very large databases of DFT calculations. They have coverage over the whole periodic table. So in some sense, to me, it seemed that maybe this dream of Dirac was kind of finally coming to fruition, right? That now we had tools that allowed us to use quantum mechanics to simulate the whole periodic table. And so I started to think, well, how far can we push these models? What are their limits? Can we start to think about these much more ambitious problems? And so I thought, what is the kind of dream thing that I've always wanted to simulate with quantum mechanics that's never really even been possible? And always in the back of my mind when I was thinking about ions in solution and things, potassium ions and sodium ions, and getting those right quantum mechanically, was the idea that one day this would be important for something like the potassium ion channel, KcsA, right? Which is one of the most important proteins in the universe. KcsA is a particular example of it that operates in bacteria. It conducts potassium ions across the cell membrane with incredible selectivity and speed. Very, very important. All of the electrical signals in your brain and your heart are coordinated by these channel these proteins conducting ions across. Um, Remarkably as well, we really don't understand some of the even the most basic things about them, right? So this is the selectivity filter. It's got this kind of narrow channel where potassium ions flow down. There's still a kind of raging debate about is water going down this channel or not, or is it just pure potassium ions? Um, and so that was the first thing I thought would be interesting to try. How good a job does Orb do at this? Which really I had no right to believe it could do anything close to this, right? Its training data consists of small crystal structures, right? So ions in, maybe a few ions in a small, highly periodic system, right? And, nothing like this very large, highly disordered chaotic system. And yet, when you start simulating it, you immediately see it does remarkably a pretty good job. I mean, it's not perfect, but if you kind of isolate the selectivity filter and run dynamics with it, you can see the potassium ions. If you apply a fairly large force to them, you can see them passing through the selectivity filter in a reasonable way. And you see all sorts of interesting physical properties, such as this hydrogen bond here between the water molecule and the entrance to the selectivity filter at the bottom there, and water molecules in this filter, right? And so this is something that's never been observed before. But as soon as you see it, it immediately makes sense and seems likely that it would have an impact on the process of whether water moves through these channels or not. So it's a very important thing to know. Oh, is this actually something that's happening? It's a very interesting hypothesis. The other thing you'll see is this flipping of the backbone here. You can see one of the carbonyl oxygens in red switches to become a amine group, bonding again to a water molecule in the selectivity filter. So this will stabilize water in the selectivity filter. This has been seen in one or two classical force field simulations, but there's never any consensus about whether it's real or not. So I think this is, again, good evidence that, yes, this is an important process going on. And something that needs to be looked at more carefully with experiments. So these observations haven't been validated experimentally yet, although there's good evidence to believe from mutational studies that they are important, particularly if you delete that threonine OH group at the bottom there. The conductivity does go down by an order of magnitude. So I'm fairly convinced that probably this is what's happening. But we're still going to wait for some experimental confirmation. But this is an indication of the kind of things you can start to think about doing with these models, right? What are the systems where classical force fields have never been able to resolve this problem? Almost all classical force fields underestimate the rate at which ions move through this filter by a factor of 10, right? Orb seems to do an okay job. So again, this is an indication that maybe we have a new class of models that can really do better here. The other one that I thought about was what is something that people don't even try to use force fields to simulate, right? Because it's just too hard. And here, enzymes is a really big category of problems, right? Where enzymes accelerate chemical reactions. Obviously, here you have carbonic anhydrase. This accelerates the CO2 to bicarbonate conversion, incredibly important enzyme in the body. Very, very hard to simulate these with classical force fields because they involve chemical reactions here, right? And here you have a CO2 converting to a bicarbonate. That's something that you need a very carefully parameterized force field to kind of get that right. No one's really built anything that can do that. There are some force fields that can model kind of proton hopping and things, but nothing that can simulate any chemical reaction that might occur like Orb can. And so that was another thing I tried, taking Orb, taking that carbonic anhydrase enzyme, just taking the active site. And in fact, this is the whole protein I'm simulating here, rather. And here you can see it actually does reproduce the formation of a bicarbonate ion from CO2 in the active site. And all you have to do is add a CO2 there and just constrain it to keep it in the site as a kind of enhanced. So there is some enhanced sampling going on. But you can see it's reproducing that reaction as exactly as expected without being driven to do it or anything. And interestingly, you get a kind of proton hopping chain occurs immediately after it forms, where it hops onto a neighboring water molecule and onto a threonine on the protein. So this was really exciting to me too. Again, we're not sure. This is a different pathway to actually the standard proposed pathway where the CO2 reacts actually with the hydroxide on the zinc. So we're seeing again something interesting, something different with Orb. We'll need to wait to see if any of these can be experimentally validated to know if it's real. But I think again, exciting times showing the potential of these tools. And the reason I did this was to kind of push the limits of the tools, see what they were capable of, to get people excited, to get other people ready to use these things, because these tools are about to get a lot better, right? We now have huge new databases, much higher level of theory, many more relevant training data configurations very close to the actual system here that we're looking at. So the forces should get much more accurate pretty soon. Again, we're so far from the training data is so far from the system, and yet still able to run stable MD, show us interesting observations. Once these models get, we train models on more specific data, I'm really optimistic that they'll get a lot more quantitatively useful. We can start to make a lot of predictions about, rates of these processes, transition barriers, and so on. Okay, and then Orb-v3, again, we're seeing improvements as well. So Orb-v2 did have some kind of, if you simulated whole proteins, it couldn't do a very good job at stabilizing the whole protein. Orb-v3 now seems to be handling that pretty well. Here we're simulating this carbonic anhydrase, the entire thing, and there's tens of thousands of atoms in solvent, and over a nanosecond, it's very stable, stays right on the PDB structure. So that's really nice with this MPA version. Interestingly, the MPA trained on materials project in Alexandria looks a little stabler than the OMAT model. So that was an interesting observation, even though the data is larger there. Yeah, so that's what we've been doing with Orb. And then the next thing to say about neural network potentials, I think, is it's useful not to think of them as just a tool for accelerating or replacing classical MD or ab initio MD. They will do that, but I think that also it can be useful to think of them as a more broader framework, right? As the score is related to the force, as we were talking about before. If you grad log this probability distribution, which is a score which is used throughout generative models, it is actually identical to the force, right? But many people have developed techniques in molecular dynamics called coarse graining, where you're not actually using a force on every single atom in the system, but you're actually using what's called the potential of mean force, or its gradients. And this is, you take X as some reduced dimensional description of the system, and then you could still use all of the tools of molecular dynamics. That's actually rigorously defined using StatMech, and this is a general strategy for simulating physical systems. So I think it's worth being wary of kind of reinventing the wheel. MD has much to learn from machine learning, but I think the vice versa is also true, where there's been a lot of thought about how to simulate and understand systems more efficiently than just brute force, all atom MD simulation. And there's a lot of parallels and connections going on that can be exploited. And I think a better way to think of neural network potentials perhaps is not as just a tool for replacing one of these things, but as a connective tissue between them, right? It's a tool for connecting scales, for taking information from quantum mechanics and using that to run all atom MD, but then also taking information from all atom MD and using that to run coarse grain simulations and even getting to larger and larger scales. And it's a really interesting question. Can we kind of use this as a tool to leverage to get up to larger scales and look at kind of macroscopic properties? And this was an idea which I've outlined before in the context of my electrolyte simulation work, where we did exactly this. We kind of coarse grained out the solvent molecules in this case, and then still trained a neural network potential on this, what's called the potential of mean force, which is the energies, the free energies now of these ions in solution. And then you can simulate electrolyte solutions much more efficiently with this approach as well, which is exciting. And now this is one of the things I'm working on with Orb is trying to use Orb in a similar way and see how we can use Orb to do enhanced sampling, which I'll have some more to say about, hopefully not too soon. Great, so where to from here? So Sander's going to talk about Orb-v3 next, but there's big new training data sets coming out now, which is really exciting. So there's a ton of work now to be done, taking those data sets and building new models that can leverage those efficiently. Another thing that needs to be done, I think, is building data sets of molecular dynamic simulations with neural network potentials, right? We're starting to see this now, but most data sets of MD are like classical force fields. And so there's bioemu and various things which are trained on classical force field MD simulation, but I think we really want to use this higher accurate neural network potential MD. So we need to start building these data sets. It's an interesting question when you start doing that. Do you improve the models more first, or is it worth starting now? But I think we're getting to the point where we need to start building these pretty soon, pretty urgently. We want to focus on developing workflows and demonstrations with NNPs, right? So not just new architectures and new models, but actually using those models or building tools to take those models and integrate them into existing actual solving real world problems. And I think working with domain area scientists is really important here, going and finding scientists who have real world problems, trying to help them simulate their systems, make falsifiable experimental predictions, rather than just trying to score well on a data set. And then we want to work on connecting all atom to coarse grain representations, trying to get to these larger scales. Integrating with LLMs is a big piece of this as well, trying to help improve the pipelines to get these simulations running, but then also automatically analyzing these simulations as well, because we're about to have a huge amount of simulation data that we won't be able to analyze ourselves. So automating that process of screening those simulations for interesting reactions and so forth is going to be really important. These are all things we're working on at Orb, amongst other things. And then architectural improvements is also important, but I think we want to avoid herding. I think this is one of the lessons from Orb-v3. Um, we want to try diverse architectures. So maybe equivariance isn't necessary at all times, or maybe there's benefits to sometimes leaving that. Similarly, we don't want everyone throwing out equivariance and no one using that, right? You want to try exploring the whole phase space of different model architectures. But a particular focus on scalability and speed, I think, is really important as well. Not just accuracy. We're not just trying to get the most accurate models. We want ones that are actually really useful. And that's one of the things that I'm most excited about Orb. It has this very low memory requirements, fast speed, which enables you to really scale the model to large systems. With that, I'll hand on to Sander. Take over.
Yeah.
Sorry, before we move on,
Yeah, sure.
like what was the thing that you showed for enzymes that we're able to do?
Carbonic anhydrase?
Yeah, so what is the prediction that you're making here, or what are you simulating?
So I'm simulating the active site of the enzyme, which is where the reaction happens. So here's the zinc atom, the zinc ion, and these three histidine groups that coordinate it. And you see the actual reaction where the CO2 converts to a bicarbonate. So they got the CO2 here, and it forms this new species, H. So you got CO2 converts to HCO3. And so that's known to happen, but the reaction pathway is actually different to the standard one. So one thing was just a demonstration that it could stably simulate this active site in this reaction. But the interesting thing is that the reaction pathway I saw is actually different to the standard accepted one, where the CO2 reacts with this hydroxide, which is bound to the zinc. Instead, it reacted with a neighboring water molecule. Now, that could have been an artifact of the way I set the simulation up, but there's actually some reasonable experimental evidence that this is a plausible reaction pathway that may be happening in the real system. In particular, there's a strong what's called a kinetic isotope effect, where if you swap the waters out with heavy water, it slows down a lot, which indicates a proton is involved in the reaction, which is not true for the standard pathway. So there is some interesting predictions here that I'm working with some experimentalists to try and confirm. But yeah.
And there's now a lot of bond breaking and bond forming also going on all the time
exactly.
in this simulation. Is this real or not?
Mm-hmm. Yeah, so what you'll see is, in particular, you see a lot of protons hopping around, which is real. Now, so these things all have a pKa, so they have some equilibria where the protons are like to be on the water molecules. So that's definitely real to the extent we see it. And there's a few examples of that happening. The bicarbonate reaction is obviously real. That's a reaction. That's a bond forming reaction. That's what the enzyme is doing. I didn't see too many other reactions other than that, other than some protons hopping on and off, these hydrogens hopping on and off, which is known to happen. Now, there is a question. It may be that these happen actually a little fast, potentially, could be one issue. So that's something, I wanted to look into a little bit more, like quantitatively, if you want to know the rates of these reactions. I'm not sure that I would trust Orb here without fine tuning. So probably quantitatively the rates aren't quite right, but that was the exciting thing is all the reactions we saw were plausible. And in the potassium ion channel, I didn't actually see any reactions happen. So which is what you should expect. There was some protons that hopped on.
If you just play this video again, isn't there an oxygen? The oxygen connecting to the carbon is the reaction that we want to see happen.
That's it. Exactly. That's bicarbonate, HCO3.
Okay.
Yeah. And then these protons, you notice the protons hopping off. The whites of the hydrogens, yeah.
So then, this sounds all super incredible, and we can now throw some substrates into an enzyme and then see the reaction happen. And are you saying this only works for this one reaction and not for others? Or
this is the only one I've tried. I think it's pretty incredible. I want to be clear. I think it's incredible. It blew me away how good it was. So I think it definitely every every enzyme should be simulated with this kind of approach very soon. And I think it will be
So
incredibly
here,
important.
did you use, is this an Orb-v3 simulation?
This is Orb-v2, yeah. So, but then
Okay.
I've rerun it with Orb-v3 and seen some of the same proton hopping things. I haven't seen the CO2 reaction happen yet, but I probably haven't run it long enough. Oh no, I haven't actually run it with the CO2 in it yet. Sorry, I've only done it with the water. Yeah, so I need to reproduce it with V3. One thing I would say is, I mean, I don't want to claim. I did actually try Rubisco where, I mean, one thing is these reactions are all much longer time scale than Orb can probe. So this is one big caveat, is that these reactions happen on a uh, typically this one happens on a microsecond timescale, but we obviously can't access microsecond timescales. So you have to use kind of what's called enhanced sampling techniques, which are ways of accelerating the simulation to try and drive the reaction to happen. So here I've just added a force to keep the CO2 close to the reactive site where I know it will happen. And it may be that Orb, also Sander will talk about some problems with Orb-v2 where with minima where it may actually accelerate. It may be a little too reactive, and so maybe we're seeing the reactions a little early, a little too fast. So there's a caveat there that maybe if you had the perfectly fine-tuned model, that the reactions would take longer. And so, yeah, there's some caveats there. It may be that you need some smart enhanced sampling techniques to make the reactions happen. But I do think that this is going to be really, really useful for understanding enzymes. I think it's going to be critical. I don't see, yeah,
the
yeah.
point why we cannot do this with non-NNPs is because it would just take way too long to evaluate even just one, just one function or one iteration of DFT or whatever to
Exactly,
compute
yeah.
one energy evaluation would take way too long.
Yeah, I mean, you never even fit it in memory, right? So you need to do a whole active site. Here I did the whole protein, which is cool because Orb has such low memory requirements. But you couldn't even, the DFT calculation, you could never fit it. Well, I guess if you used a huge supercomputer, maybe, but it would be too slow. Yeah, you couldn't do, I mean, people have done a lot of static DFT where they'll do like a few point single frame calculations, right? Or try geometry optimize like some representation of the active site. It'll take like, I don't know, 50 atoms or something, but no one's managed to be able to simulate this whole thing. And then classical force fields, people have simulated enzymes with classical force fields, but something like this bicarbonate reaction, it's very, very tricky to get that right because you've got all these parameters you need to you would need to fit a huge number of parameters, and no one has really built a force field that can do that. They have built force fields that can do the proton hopping where the hydrogen hops along, but nothing can really look at this reaction here. Like, see how the bending, the angle changes as it reacts? Like, that's really tricky to get that right. You need to build a force field that kind of has this dynamic angle that can change and things, but it just drops straight out of the neural network potential that, oh yeah, this is reacting with the water now, you're going to get this bent conformation.
Okay, I think that is a good motivation to then continue how does the thing work.
Yeah, let's jump on to Sander.
Right. I'm gonna steal the share here because I don't think I'm connected to the.
Yeah, I'll just stop sharing. You can take it.
Yeah. Does this work? You guys see the screen properly?
I see a screen now.
Yeah, cool. Okay.
I don't, maybe.
Tim, you all right? Did you see it too?
If everyone else can see it, I assume it's fine.
I assume it's fine.
Yeah,
okay.
Let's go ahead.
So the idea is that I briefly go into I guess what we're trying to solve with Orb-v3, and kind of how we did it and how we in general look at developing these NMPs. So to recap, what we're trying to do is we're trying to bypass quantum physics. Quantum physics dictates how you can effectively associate an energy function to a set of atoms they have atom identities and they have coordinates x. And so why is this a useful thing to do? Well, so statistical mechanics dictates that once you have this energy function and you exponentiate it, you get something that's called the Boltzmann distribution. And from this Boltzmann distribution follows basically everything else in good approximation. So sampling this Boltzmann distribution is what can give you physical properties and other types of predictions. And so really the NMP basically bypasses the need to do quantum mechanical energy evaluation. It's just a neural network, the E of X. Now the thing is, this looks nice, and so the NMP just needs to learn the energy and its gradients. But there's a big caveat, and that's that the Boltzmann distribution is exponential in the energy, and that kind of means that certain areas of, or certain configurations, certain atomic configurations are going to be much more important to describe accurately than others. And it can give rise to some weird, weird behavior in certain potentials. And so traditionally, I think the field has looked at performance on benchmark data sets, and they report RMSEs or they report F1 scores. And there are a lot of models that do very well on these indicators, but in fact, that does not translate into real predictive power. And this is something we realized in this third generation. And what we focused on in this third generation was actually going for predictive power rather than some performance on some benchmark. Right. So what is an example of a property that is very, very sensitive to a very local a very small fraction of the configuration space, but which is actually hugely important for physical properties? And there's a few of them. First is a bulk modulus of material. So if you consider a material, iron, it's just atoms stacked together. They are described using a unit cell, this purplish parallelogram. Now, if you deform the parallelogram isotropically, you will get, and you monitor the energy change as a function of that deformation, you'll get something like this, right? The energy in good approximation evolves quadratically with the change in unit cell volume. And for a very strong material, very small deformation is going to give rise to high energy changes. And for a less strong material, the curvature is going to be much lower. And the experimentally measurable so-called bulk modulus of material actually relates very strongly just to the curvature of the energy surface. And interestingly, we don't need to do sampling to get a curvature. We don't need to take multiple points. We just need to take a second order gradient. And this is traditionally how many computational pipelines estimated the bulk modulus, for example, using DFT, because it was computationally very efficient. Another example of where, a surprisingly small fraction of the configuration space is relevant for this physical property is thermoconductivity, which has recently gained some attention in the NMP community. So thermoconductivity basically tells you, if you put in heat on one side, how fast does the heat kind of come out on the other side? Heat is just the movement of atoms. And so we're asking ourselves, how fast can this transport through the material? Now, basically what you're asking yourself is, if I start wiggling atoms on one side, how fast are they going to start wiggling on the other side? That is the intuitive picture you can associate with this. And so what makes atoms wiggle? It's a force. And what we're wiggling is the position. And so really what we're asking is, what is the change in force on one side if I'm wiggling on the other side? And doing some chain rule, this effectively just implies, again, a second order derivative, but now not with respect to the unit cell volume, but with respect to atom coordinates. The bottom line I'm trying to talk through here is that a certain class of physical properties depend on second order derivatives. And if we're following this scheme and we're just like blindly fitting energies using a machine learning model, we are not really guaranteed that we're going to get those curvatures right. This is like kind of like implicitly correct, but it's possible with some pathologies that you get this manifestly wrong. And this was the case for Orb-v3. This is still the case for many other potentials. And this was kind of our main target to solve for Orb-v3. Right, so Orb is the quantum mechanical energy. So its derivatives determine these physical properties. Orb-v2 had this very curious thing where it was pretty accurate if you would look at basic RMSEs, but it got the minima wrong in the sense that they were a little too flat. And the tricky part of that is that this won't show up in an RMSE or in a loss function. If your loss function is typically a combination of energies and forces. If you get them wrong just around the minimum, that's not really a problem. You can't really solve that by training longer, intuitively. And so this is this was an interesting observation. Now in Orb-v3, we fixed this. Orb-v3 describes potential energy minima just like you would expect and just like you need to in order to get physical predictions. And I'll get into how we achieved this in the next few slides. The answer to basically solving this issue was surprisingly disappointing and yet not so much. First step is just you need more and better data. And the second step is you need a whole lot of engineering and fine-tuning during training to really make this work. More and better data, in our case, involved OMAT24, which was different from many of the established training sets because it includes finite temperature samples. It includes a much broader coverage of your Boltzmann distribution, which means it just implicitly imposes a lot of regularization on your model during training because it sees a larger variety of configurations, so it's harder to overfit. Now, this is kind of disappointing because it's not really like, some cool theoretical trick that we've applied in order to fix this, but it is interesting because the whole gamble, which turned out to be quite successful, the whole gamble with Orb is actually that an unconstrained architecture, if given enough data, can succeed, can perform just as well as other constrained architectures, with the added benefit that you gain a lot of performance. And so really, Orb-v1 and Orb-v2 we were just still in the regime where the amount of data that was available, which was MP-Traj, Alexandria, was not quite enough to really fully resolve it. And we've moved beyond that now with OMAP. We are in the regime now where we have enough data where unconstrained architectures can really shine. And that's very nice. But of course, all those months were not just spent training on OMAP. We completed a lot of architectural improvements. Most of them are like small things, but they happen to matter quite a lot. The embedding of your distances in the of your distance expansion between the atoms. It's playing around with hyperparameters of the model architecture. It is switching your loss function from something that's L1, which is non-equivariant, to something which is both locally equivariant and also robust to outliers, which is the Huber loss. It's like very technical things like making sure your batches are always more or less the same size, both in terms of number of systems, number of atoms, and number of edges. Building in some physical priors as well. So these are all like kind of small tricks that we needed to do in order to go from Orb-v2 to Orb-v3 and really, squeeze out the last bit of performance. One, or I guess maybe the most interesting improvement that we did was something called Equigrad. And this is a theoretical, let's say, a simple theoretical trick you can do during training to really improve the equivariance behavior of models that are by construction non-equivariant. And this proved to be quite important. So Orb is non-rotationally invariant. What this means is that if you give it a system, it'll spit out an energy. If you rotate the system, but otherwise keep it exactly fixed, and you again give it to Orb, it might spit out a slightly different energy and slightly different rotated forces, which is ideally not what you want because physics says, no, space is isotropic. There is no preferred direction. Every direction is fully equivalent, which means all results that we derive from Schrödinger's equation should not depend on the orientation. And so this invariance is obviously embedded in the data. So implicitly, if your model is not constrained, you're going to learn this. But we've observed that with Orb, that's not enough. You need to somehow incentivize the model more explicitly to learn rotational invariance. So how do you do this? Well, the first step is like, how can you quantify rotational invariance? Well, what you could do is you can consider multiple rotated copies of a system, and you can check the variance in the predicted energy, or you check the variance in the predicted forces, which is an approach that past authors have taken. I think Michael Brunstein has a paper about this. That's possible, but that's very expensive and kind of cumbersome, and also not really necessary. Intuitively, the way we think about non-invariance is just an infinitesimal change in energy that happens when you would rotate the system by an infinitesimal amount. So it is kind of like a derivative, except that it's not really clear how to take the derivative, especially if I assume most of us do not have a math background, or do not have a very strong theoretical math background. We all have an engineering math background. And so in practice, though, once we're able to kind of pinpoint exactly which derivative we want here, the idea is that you just add a regularization term to your loss function, which tells the model like, okay, don't make your prediction depend on the rotation. But we do this not by considering multiple rotated copies or by considering data augmentation. Those are established strategies. That's simple. We do this by taking a clever derivative, basically. And this is described in the paper. The crux of it really is actually derived from quantum mechanics. I was a TA for an undergraduate quantum mechanics course. And, in quantum mechanics, you have the concept of a generator of a transformation, which is basically the thing you put in a matrix exponential that generates your transformation. In the case of a rotation matrix is unitary matrix. So what you need to put in the exponential is this Q-symmetric matrix. For those of you who are familiar with the way PyTorch potentials compute the stress, this is very similar to how stress is computed by models like Schnett and Mace and Equip and stuff. It's just that we don't do it for stress, we do it for a rotation. What it allows us to do is really quantify the amount of variance that there will be at one specific configuration due to any infinitesimal rotation. And subsequently, we can use that to, add a term in the loss function, this third term, to quench it, basically, to tell the model, don't be dependent on the rotation. So that's Equigrad. And so to illustrate this, so if you include Equigrad in your training versus if you don't include it, we really observe a massive reduction, like a factor of 10 reduction in the dependence on the orientation, to the point where it goes below the noise level of basically the error in our forces and energies. At which point you can say, okay, this is kind of trivial now. This problem is not really there anymore. And so it's a soft way of including equivariance, but we found that this is effective and also important if you're working with highly symmetric structures.
Sorry, is this also helpful for other things besides just the let's say rotational?
Yeah, you mean other types of symmetries that would not be guaranteed?
No, not other types of symmetries, like some properties that we care about, or like metrics that you care about in the end, some downstream evaluations. Like, of course, if I have a loss that encourages the model to be equivariant or invariant with respect to this particular symmetry, and then you like measure the error in not being invariant with respect to that symmetry, then yeah, that error gets better. And we know that in principle it should be, if we have a perfect energy function, then this should be working out, or you should have this symmetry baked into your model, or not. Your model should satisfy that symmetry. But does it now, adding this loss, help your downstream tasks, your downstream performances?
Right. Yes, it does. So one of the performance indicators in MapBench is basically the optimized geometry of crystals, as in not just the final energy you're arriving at, but actually the geometry, the XYZ of what your model thinks is the potential energy minimum. And what we found is that even with models that they are by all metrics actually quite invariant with respect to rotation, but when it comes to these very specific things like optimized geometries and crystals that are highly symmetric, the loss of exact rotational invariance means that it's bad at doing crystal symmetries properly, and it means that your optimized geometry is quite non-symmetric. It's not off by much, but it's measurable. And well, we found that if we included a small amount of Equigrad, so basically, weight that term very lightly in the loss function, we noticed two things. Like, one, you don't compromise on the performance on your energy and forces, and two, the downstream task, which I think you're referring to, which is in this case, was like, okay, accurate geometries at the minimum improved quite significantly.
Do you think or does the Equigrad loss rely on the target or the output of the network being forces? Or
No, in fact,
also...
it's so this Equigrad is computed by doing autograd on your energy output. So this was done during training a conservative model, actually. Yeah.
I see. Okay.
Which I'll get to in a minute. So right. So translational invariance is built into Orb. It's relatively easy to build in. Rotational invariance, we have eventually settled on doing it in a soft way using Equigrad. The reason for doing this is that usually those types of models are easier to implement in a more performant way. I think recently there have been some libraries from NVIDIA in which they try to implement equivariant operations in a highly efficient manner. So far, we've not seen them make models like Maze much faster than ours, but that might actually change in the future. We are aware of this. But other than this, there are actually other, let's say, concerns in the construction of these models that, where let's say ML practitioners have the choice of going for the very accurate approach, which might not be as performant, or for something more approximate. And then the question is, how can we decide on this balance, number one, and number two, at what point are we losing accuracy in physical predictions? Because as I've started with this presentation with, it's not so easy to decide this based on simple error metrics on benchmark data sets, because, well, those are easy to satisfy anyway, and they don't actually translate into real predictive power. And so the two other axes basically that we can consider here are, how do you compute forces? Do you do this by taking an exact derivative, as in an exact automatic differentiation of the output energy node, or do you, just predict a n/3 matrix which represents your forces? And there are obvious downsides to doing the direct prediction, because forces, it's a conservative vector field. Like if you do a PyTorch prediction of those forces, it's not going to be conservative. It might not be translation. It might not be momentum conserving. Sorry. So there's a lot of concerns there, but still, the question is, can you do it? And then the final one is, how do you construct your graph? So the input to these networks is not just raw atomic positions, it's actually atomic positions, which are then converted into a neighbor graph, a radius graph, which basically encodes like how the distances between each of the nodes, and there are only edges between neighboring nodes. And you can consider this graph construction just in the raw way, and in the way in which many models do it, or you can try to sparsify it, because intuitively it's obvious that you might not need all of the edges in the graph. You might try to, let's say, sparsify the operations you're doing. And also that is a axis in which you can trade off accuracy for performance. The bottom line is that we chose those last two things. We didn't make one choice. We made a few models available, and we believe that each of those models is actually useful to the community because they just represent a different trade-off between accuracy and performance. And what I'm showing here is this trade-off on one metric, which I think is KcsA, but my screen is kind of in front of it, so I can't see it. Yeah, it's the KcsA. So this is a metric that represents the accuracy of your model in predicting thermal conductivities, which was a metric that Orb-v3 was originally very bad at. And basically, the point we're trying to make here is, yes, you're losing accuracy if you're going to a sparse graph, and you're losing accuracy if you're going to direct force computation, but the gains are incredible, number one, and number two, we can still be very accurate. We can still be competitive with other models. And this is an important message, I think, that we wanted to get out with this release. We've done explicit benchmarking in comparison with other models that were out at the time of writing the paper, which was a few months ago. We've done this as a function of number of atoms and system size. So I'm just showing one result. For the full results, you have to I'll refer you to the paper. But basically, the red and blue will be Orb versions, and then everything else will be other models. And the point is not that we are faster in the forward pass, but also that the memory consumption is much lower. And this allows Orb to go to much higher systems than other models usually. Then finally, the goal of doing all of these things is not to win in benchmarks, but to make predictions on physical properties. And so we've made that a priority in this release. So we tested Orb on predicting physical properties, and we've done so based on a few, let's say, common properties that are available and for which workflows exist. And these are properties based on calculations done using PhonoPy. And so we can clearly see in the bottom half of the table that are the trade-offs that I just mentioned, being, do you compute forces using gradients, or do you compute them directly on one hand? And secondly, do you consider all of the full graph, or do you limit the number of neighbors? In this case, this is denoted by inf or 20, inf meaning full graph, 20 meaning the sparsified one. And so clearly the accuracy in the prediction is kind of going down, but really not so significantly. And most importantly, the performance is much better. Either way, we believe that all of these models can be useful to the community, so we make them available. But yeah, the message remains, like, each of these has its own area of application. I think that's pretty much it for me. So yeah, if there are any questions, I'm happy to.
Well, there's nothing in the chat and nothing from my side.
Cool.
Well, one thing actually. So your whole exposition assumes that I know Orb-v2. Can you say in 2 words or 2 sentences, how does Orb-v2 work?
Yeah. That's actually a good observation, and I kind of realized at the start of the meeting. Right. So what separates Orb-v2 from the rest? I am going to assume basic familiarity with graph neural networks, because that would be, I guess, maybe a bit too much of a detour.
Yes, please.
what separates Orb-v2 from the rest is that Orb-v2 does training in 2 stages. There was one part of training, which is the initial part, which is pre.
Okay, sorry. Just probably maybe something like it's a graph neural network. It takes as input the 3D coordinates and not like some distance encoding or so. It literally takes these 3D coordinates as input in a non-equivariant manner, and then it predicts an energy, and at inference time you backpropagate through the thing and use the gradients of the energy to update your coordinates and run inference.
Right. Yeah. So
Okay.
exactly that. I guess a
But it
good
does
reference
have
for
the
this would be Hitchhiker's Guide to GNNs, which I'll link in the chat because I think it's a good recap of this.
it does have a denoising pre-training though, right? Which is what Sander was just
Yeah,
saying.
which is what really sets it apart from everything else.
Yeah.
But yeah, let me just link this paper.
So before we just train it to predict the energies of some points where maybe you also have a loss on the forces and not just the energies, you also train it as a diffusion model.
Effectively, yeah. The force and energies don't even come into play in the first stage. So it really just takes in optimized geometries, it noises them, and it asks the model.
Yeah.
Can you remove them?
That is what, before you train it with forces and energies, you train it with that. And then you train it with forces and energies, right? Or only energies.
And then we train it with forces, energies, and stress. Yeah, then we fine tune.
Okay. Stress.
And
All right.
one key insight is you can leverage a much bigger database for the denoising because you don't need the DFT calculations. So we have big databases of stable molecules you can then say, which I think is probably some of the reason for its generalizability to these biosystems I'm talking about, even though I haven't rigorously demonstrated that, but that's my hypothesis.
All right, then I think everything should be all set to move on maybe. And could you talk a bit more about the distillation of the conservative models to the direct force computation? How did it work and what did it take to work? Do you know what that is about?
Yeah. We don't actually so the direct models are just trained in we don't do distillation actually. They're just drained directly to the raw DFT targets. We've experimented with distillation, but I think that I'm pretty sure the current models that are released are non-distilled. So invariably this means that because forces, which people may or may not know, the energy is an invariant quantity, but because forces represent a gradient, that becomes an equivariant quantity, as in it inherently rotates with your system. So having that be predicted by your model is much less trivial than just having an invariant energy prediction. Fundamentally, I don't think we didn't do
Ben did at the end, we included, I think Ben had a distillation of the direct where you
right, but we
the
did
direct
not.
using the
We ended up separating them again, actually.
Oh, okay, yeah. So the final models don't.
Yeah.
Include that.
But so, yeah, I guess the difficulty there was that, especially when you're doing calculations like these, the current slide that's showing, which are second order calculations using PhonoPy, very small differences in input atomic positions translate to very small forces, and it's quite difficult to resolve those with direct force models. So getting these numbers so accurate was quite challenging. But unlike what people say in literature, it's not a matter of really, engineering your architecture to be, physically inspired like the escape architecture. We found that if you have the right amount of input data, that it kind of just follows from the model. I've experimented myself with certain, physically informed force predictions, which kind of directly impose net zero force, net zero torque, and things like that. I've actually found it to be quite difficult to beat our standard fully agnostic direct force predictions. And that's just because we are, again, in a regime where we're sufficient data, we have sufficient scale to learn this. Yeah. Does that make sense?
Yeah. I think then we maybe also at some point want to talk about the new data, OMOL, and how big of a change that is in the amount of data we have. And
Yeah. So it's, what was it, 83 million molecules? It's a lot. I think it's especially interesting because I'm not sure if they publish the full electron densities, but they do publish partial charges. I think spin density as well.
They're planning to, I think, yeah. Apparently there's petabytes
Yeah.
of charge density. This is gonna be a lot
Oh,
of
yeah. Okay. So I think there's a lot
many more
there.
petabyte.
For pure NMP training, I think it's interesting. I don't think it'll be groundbreaking. I think it's just an evolution again. We are, of course, very interested to see how Orb does when we include OML during training, because at the moment it's trained purely on crystal structures. Our performance on molecules is actually not that bad. It's pretty good. There's this, what is it, GMTKN 55 or something data set which we benchmarked against, and on which we showed reasonable performance. But yeah, I think OML is another step function, just like OMAT was. I don't think it's a revolution. I think it's just, another step up, another scale higher.
Yeah, I
So
mean,
what is the OMAT data? What sort of molecules do you have in there?
Right. OMAT takes Alexandria and then rattles it, as in applies Gaussian noise on one
That
hand.
doesn't tell me anything. Alexandria.
Right.
it's
Just is
another
it
crystal structure
proteins?
database.
Do you have?
Right.
Okay, so
Right,
it's
right, right. Yeah. So it has materials. So there's this thing called Materials Project, which is a big online database of materials, including a DFT calculation that are run on those materials. And they are quite, or they try to be quite rigorous, as I think they do a good as job as you can, really, in trying to really be systematic in the DFT setting so that they're consistent with each other and that this database is sort of ready to train things on. The issue with that database is it considers materials as like a single structure, basically, or an optimized structure. It does not fully do or take into account the fact that actually what matters is a whole distribution, being this Boltzmann distribution, which means
Yeah.
you need your material at various configurations of the atomic positions, and only.
And do you find like training on OMATs to also help for, like for example, these enzyme simulations?
No, that was an interesting thing that it doesn't look like the OMAT helps that much. So in particular, a few things we found was um, if you look at, I think Sander's plot there, where you have the different models, sometimes the MPA model is better than the OMAT one, even though at least on that KcsA, at least on this one benchmark, even though the OMAT data is much larger, which was interesting. And then another thing we found is that if we included all of OMAT, actually some of our out of distribution data got out of distribution predictions got worse, in particular like dimer energies were worse with all of OMAT. And we found actually dropping all of this rattle data and just keeping the ab initio MD data gave us really nice smooth out of distribution, these pair potentials, two atoms together, trying to predict their energy. So there's some interesting kind of artifacts coming in with that. So it's not clear that bigger data is always better. The reasons for this, that probably what I suspect is going on is that DFT can have some convergence issues and can converge to different states, right? It can get trapped in local minima essentially. And so if some of that, and I saw some other papers where they've shown this, that there's some data in those data sets where maybe the DFTs converge to an unusual state. And so you probably need to be very careful about cleaning the data. It's probably what we need to do. So OML may be, but I'm not certain about exactly what's going on there.
Yeah, what is the amount of protein and small molecule data that you are training Orb-v3 on right now?
0.
Okay.
Yeah.
And
there's no protein, yeah.
Orb-v2 as well?
None, unless you include the pre-training, the denoising may have some, it won't have any whole proteins in there, but it may have some protein like, it'll have amino acids and things in there. In the pre-training, the denoising.
So then, since there are many molecules and proteins in, like for your enzyme simulation, shouldn't then training on OMOL, which now at least includes some proteins and some small molecules, shouldn't it help a lot?
Yeah, I think it should help a lot. The other exciting thing is it's a substantially higher level of quantum chemical theory. So it's not PBE anymore, which is what we call like the kind of one of the second rungs of the ladder. It's a hybrid, so it should be much closer to kind of gold standard quantum chemistry. It should be close to chemical accuracy, hopefully. So I'm hopeful that you could potentially make some quantitative predictions with it. But it will be, as Sandra said, I don't think it'll be necessarily a step change. I think it will be, well, we'll see. But I think it's probably likely just to get you to that quantitative point. And I think that could be a step change as well. If you can get to like quantitatively precise predictions of things, then you can really start to nail down experiment and really demonstrate that these things are correct.
And so to me, it sounds like previously there was zero data to train on that contained small molecules and proteins, and now there's at least some data.
No, so there was SPICE and any data sets. So there was quite a bit of big quantum chemistry data sets.
Yeah.
So yeah, that's why it's not. It is big and it's exciting.
And why didn't you
we'll see how
include those when training Orb-v3 or Orb-v2?
Yes, I don't know if you want to talk about the Sander, but it's actually quite a tricky issue how you combine different data sets with different levels of DFT theory, and it's non-trivial. So even OMAT and MPA, even though they're both PBE level of theory, these are two materials databases of crystal structure databases with DFT. They have slightly different what's called pseudo potentials, which is a technical thing in how the DFT is done, which means that they're not directly comparable. And so you need to be very careful about, you can't just throw all the data together, basically. So that's why there are some people who have tried to train these models. Yeah, we use all of these data sets and you use basically a multi-headed approach. I think is probably one promising way to go. But it's non-trivial to do that with Orb.
Very
that's
interesting.
something we're looking into. Yeah.
Doesn't UMA do that as well?
Yes, I think so. Sander, does UMA do it? UMA, this latest one that just came out.
Yeah, I think.
Yeah, it has this mixture of experts, right?
They might do multi-fidelity, but I think what they're mainly known for is to, let's say, partition the computational work so that you can very quickly get to the, that you don't have to, let's say, first learn the full periodic table before you get to an accurate prediction, basically.
Okay.
Yeah, you can use it with pre-training. There was a question in the chat. Someone just asking how does it break rotational invariance, which may be worth answering.
Right. That's a fair point. So what Orb takes as input are the atomic coordinates of your atoms, and then we use that to construct a graph of your system. So if you consider an H2O molecule, then the graph of such a system would be, each node of the graph would be H, H, and O, and then the edges in the graph would be the connections between H2O. The way these edges work, because of course you somehow need to encode the local geometry of your H2O molecule, meaning the angle. And so these edges, they actually embed the relative distance vectors, the unit vectors, sorry, not the unit vectors, the distance vectors between those two atoms. So you really are embedding like direct XYZ information in that graph. And so if you would rotate your molecule, then even though internally nothing really changes, the angle wouldn't really change, but in math, in numbers, your XYZ representation would change just because it is what's called an equivariant representation. And Orb is decidedly, how do I say, it takes a very naive approach, but with a very conscious naive approach, which is we don't care about that. We assume that the model can actually learn that if you rotate it, that XYZ changes, but that actually internally nothing will change. And so this means that the architecture, even though the data that is trained to is rotationally invariant, so it will learn to be rotationally invariant, it won't strictly be rotationally invariant, which is why we say it does break rotational invariance. This is very, very hard to explain in words. Yeah,
it's one of those ideas. I mean, this is kind of when I first heard of it, I think point edge transform was the first model to do this, where it's raw distance vectors, and it's kind of like no one even thought to try it, I think, because it's just like that's obviously a bad idea, but it turns out it works fine.
There are actually quite a few models now who are rotationally non-strictly invariant. And the main motivation being computational efficiency.
Okay, so I think in the UMA paper they have like just different heads for different tasks, where tasks are materials, molecules, organic materials, and stuff like that.
Mm-hmm.
Yeah, does OMAT, no, not OMAT, your MET, whatever data set, does this include organic materials?
Yes, to some extent.
Okay.
So it's, materials they can encompass some organic interactions, right? So it's not entirely fair to say Orb did some magic and suddenly extrapolated to molecules, right? It's of course that information was somewhat already in the data, just not really explicitly.
No, I mean that's that's good, right?
Yeah, I mean, there's a
As
huge amount
someone,
of carbon
yeah,
molecules and hydrogens and things in there,
Yeah.
but there's no large disordered biomolecules.
cool. Then, yeah, this is very interesting, especially this data combination difficulty. Sounds like there are, or solving that problem would be pretty cool or pretty important. Yeah, or quite useful.
Yeah. Yeah, definitely. There's a lot
You
of problems to be solved. Yeah.
Are you quite familiar with the OMOL dataset and know like how much small molecule protein data is there in the mix next to the materials and organic materials?
We're ingesting that data right now, actually, and we're going to be experimenting with it. So I guess, yeah, stay tuned. I don't know the numbers by heart. All I know is that it's 83 molecules, 83 million molecules. Yeah.
I've got it here. Yeah. So it's 20% biomolecules, 20% metal complexes, 34% electrolytes, which is pretty cool. I'm an electrolyte guy, so it's very exciting. And then within that, yeah, there's a bunch of breakdowns.
Yeah,
Yeah,
but
so it looks
for
like
these
they're trying to
numbers,
be kind of even covering.
it always matters a lot for what is the diversity as well.
Yeah. And I've used a ton of different techniques to generate the data. So it'll be, I imagine you probably don't want to just throw all that data, maybe not, but into one bucket. I mean, yeah, there's a lot of things to try out in terms of, yeah, screening that data and data cleaning and things and seeing what exactly that gets you the best performance.
Are there any other slides that you wanted to show today?
Not really, but maybe I think there's like one more question in the chat, which I think deserves a response.
Yeah, definitely.
So I think the first one, which I skimmed over, but I should clarify what I meant. So indeed, we mentioned distillation of the conservative model into the direct force model, which we did do, but not for the models that I've shown you here on the slide, and also not for which are the models we intend you to use, being the models that are trained on the largest and most high quality data. We did do it in order to be able to show results on the benchmark that is used nowadays by the community in order to judge models. So it's only for those specific models, the MP-Traj ones, which I think are available on GitHub, but by default you would have to look for them. So for those models, we noticed that fine-tuning on MP-Traj data was quite difficult with the direct forces, just because they seem to overfit. And this is just a result of having bad data, limited data. MP-Traj is a relatively old data set. It was great at the time, but now we've kind of moved on. But so that benchmark that I'm talking about kind of relies on us having to do this MP-Traj only stuff. And so effectively there we did do a bit of distillation, yes. So yeah, that is the full nuanced answer. I hope that clarifies.
Then the longer one, do you want to go for that?
Yeah, sure. So the rotational variance can be reduced to something below the energy RMSD. Yes. So a reasonable lower bound in rotation error was around 1 MeV per atom, I think, but I have to check back the plot because I think it'll show here. Yes. So the red one, that's the actual OMAT model, or one of the the actual OMAT model will have similar metrics than the ones shown here, and it's about 0.2 MeV per atom. I think 0.2 MeV per atom is around 1 kilojoule per mole or even less, I think. Which I think we computational chemists usually agree as being chemical accuracy, as being like, okay, you've done a good enough job in describing your energy surface. So effectively what this means is that the error due to breaking rotational invariance is slightly less than, let's say, the floor, the noise floor that we consider typically in quantum chemistry, which is why I said, we believe this is okay. I don't know if that sufficiently answers the question. Symmetry is more important than numerical accuracy. Yeah, so exactly. So the only place where we would really notice the breaking of invariance would be when you're doing like highly symmetric calculations. So for example, these thermal conductivity calculations, they do exploit the space group symmetry of materials. And it was really there that that's where the idea of Equigrad kind of arose. That's why we designed it, just to be able to do those calculations while exploiting symmetry. We've also noticed that you can tell PhonoPy just don't exploit symmetry, as in like, okay, you're not working with a rotationally invariant model, so don't exploit it. And you can just, you can run the calculation as well, and you will get okay answers. So it's not a necessity. Yeah.
I do think this point about you may get a preferential drift in one direction. I think that I have seen some evidence of that in MD, so that is potentially a concern there. So
but that's translational, right?
I assume it's caused by translational. Well,
but we are translationally, like that drift was I think that was a bug in past models. We Orb-v3 does not do drifts right now.
Okay.
Okay,
yeah,
cool.
I think you could get this one, but yeah, that's right.
Any other points that we should talk about today?
No, I think that's pretty good. I should probably go good.
Then I want to thank you a lot for this nice overview. Yeah, it's a good notion of what is going on and where are these force fields at right now, and maybe yeah, I guess in the Yuma paper I didn't now see so many evaluations from which I could be like, now we can basically simulate an enzyme, but we need this and that much more speed up to be able to actually do it usefully or something like that. But yeah, how long did it take you to run your enzyme simulation?
Just a few days on a GPU normally. Yeah, I don't know how fast the UMA models are. They don't really have any speed benchmarking as far as I can find. So I suspect that, I mean, so yeah, some of these models are not built with speed in mind. So some of the models on the data bank will be not very practical for running large scale MD. They're designed to score well, basically, or to be used as a DFT replacement. I'll have to look into UMA about how speed. Oh, here we go. Speed. We've got inference time per second. Oh, it looks pretty good. So 16 seconds. I can't do the conversion in my head, but I think potentially, definitely, once we, it should be feasible to run some enzyme simulations with models trained on this database.
Yeah. Okay. Cool. Then yeah, thanks. And if you want to say any last words, now would be the time. Otherwise, I would let you go to sleep, Tim.
Yeah, sounds good. No, thanks very much for organizing again. And yeah, feel free to reach out with any questions.
I'll link the PDF of the Orb-v3 paper, and in that you'll find email addresses of us, so you can always reach out if there are any questions.
Sure. The paper is linked all over the announcements of the reading group, so should be findable.
Oh, okay. So people should be able to find us then. That's great.
Then, thanks a lot. Hear you around. Good night and nice evening.
Yep.
Thank you.
Enjoy.
See you later.